I'm Dr. Roger, and today we're looking at differential equations, in particular the solutions of systems of differential equations. This matrix equation is equivalent to the system x prime equals 1x minus 2y, and y prime equals 3x minus 4y. But we typically solve these in matrix form, and the first step of solving a system of first-order linear ordinary differential equations is to write in the form x prime equals ax, which is this form, and then find the eigenvalues and eigenvectors corresponding with matrix A. So to find the eigenvalues, we'll set the determinant of matrix A minus lambda times the identity matrix equal to 0. So that's the determinant of 1, negative 2, 3, negative 4 minus lambda times 1, 0, 0, 1 equals 0. Determinant of 1, negative 2, 3, negative 4 minus lambda 0, 0, lambda equals 0. And that is determinant of 1 minus lambda, negative 2, 3, negative 4 minus lambda equals 0. The determinant of a 2 by 2 matrix like this is the product of the main diagonal minus the product of the off diagonal. So that's 1 minus lambda, negative 4 minus lambda, minus negative 6 is plus 6 equals 0. Lambda squared plus 4 lambda minus lambda is plus 3 lambda, minus 4 and plus 6 is plus 2 equals 0. That factors lambda and lambda, 1 and 2, and they're both positive. If a product equals 0, either the first factor is 0, so lambda equals negative 1. I'm going to call that lambda 1 because I need to distinguish my eigenvalues, and that's my first eigenvalue. Or if that first product is not 0, the second product has to be 0. So lambda equals negative 2, and I'll call that eigenvalue lambda 2. The subscripts happen to match the absolute values, but in general lambda 1 is just one of the eigenvalues, and lambda 2 is just another eigenvalue. You don't match the subscripts to the values themselves. Corresponding with lambda 1, eigenvalue 1, we have the eigenvector, and for eigenvectors, A minus lambda times the identity times vector, I'm not going to call it vector x because x is actually, the vector x is my solution. I'm going to call it vector xi. Xi is a Greek x equals the 0 vector. So matrix A minus lambda times the identity is 1 minus negative 1 is 2, and negative 2, 3, and negative 4 minus negative 1 is negative 4 plus 1 is negative 3, times C1, C2 equals the 0 vector. And the first row times matrix C equals 0, so 2C1 minus 2C2 equals 0. Moving the 2C2 to the other side neatly, I get 2C1 equals 2C2, or C1 equals C2, and the second row gives me the same equation. I cannot find a unique solution, but I don't need a unique solution. I need any non-zero vector for which this is true, so I'm going to choose C1 equals 1, then C2 is also 1. And my first eigenvector, which I'm going to denote as vector xi with a superscript 1, is the vector 1, 1. In some fields, there is a convention that eigenvectors always have magnitude 1. The magnitude of your eigenvector is the square root of the sum of the squares of the two components. So that would be root 2. And if your field has a convention that eigenvectors always have magnitude 1, you would multiply this eigenvector by 1 over its magnitude to get eigenvector 1 under those constraints would be 1 over root 2, 1 over root 2. You might do this, for example, in multivariate statistics, but for the purpose of my videos, I will ignore that and assume it's okay for eigenvectors to have magnitude not equal to 1. Now, erasing this part so I have the board space. Let's find my second eigenvector. Lambda 2 was -2. I should not have erased until I wrote that down. And so A minus lambda times the identity would be 1 minus -2 is 3. And then -2 minus 0 is -2. 3 and -4 minus -2 is 2. Times C1, C2 is again the 0 vector. And that gives me 3 C1 minus 2 C2 equals 0. And I'm going to choose a value, C1. I'm going to make C1 2 because if I swap the coefficients, and flip the sign of one of them, that'll give me 3 times 2 is 6, -2 times 3 is also 6, and 6 minus 6 equals 0. So that works, and that gives me eigenvector 2 is the vector 2, 3. Once you have the eigenvalues and eigenvectors associated with x prime equals ax, the vector equation, your solution, the general solution, is vector x equals c1 e to the lambda 1 t times eigenvector 1 plus c2 e to the lambda 2 t times eigenvector 2. So the work of solving homogeneous linear systems of equations is all in the process of finding eigenvalues and eigenvectors. So this solution is x vector is c1 e to the -1t times the vector 1, 1 plus c2 e to the -2t times the vector 2, 3. Now, an obvious question is, what does that mean? In the x1, x2 plane, and I'll erase this now that I have my solution. In the x1, x2 plane, the vector 1, 1 is in this direction. The vector 2, 3 goes over 2 and up 3. And both vectors are passing through the origin. Since both eigenvalues are negative, that means if we started on eigenvector 2 here, as t increases, we move inward along that eigenvector. If we started on eigenvector 1, as t increases, e to the -t times that vector moves toward the origin. your component in both directions decreases in magnitude as t goes to infinity. The other question is, what do the trajectories look like if you have a linear combination of these? So if you started out here, which is a positive number times eigenvector 1, and then a negative number times eigenvector 2, the component of both will go to 0, but since the eigenvector 2 has a larger magnitude for its eigenvalue, e to the negative 2t goes to 0 faster than e to the negative t goes to 0, which means a trajectory that starts here will move toward this eigenvector and then toward 0. So it will do this. The component in the direction of eigenvector 2 goes to 0. The component in the direction of eigenvector 1 goes to 0. But the component in the direction of eigenvector 2, which is away from eigenvector 1, goes to 0 faster. So we seem to move toward eigenvector 1 and then almost along eigenvector 1 toward the origin. If we were up here, we would do this. And our distance away from eigenvector 1 is always decreasing, but it produces this hook-like behavior in these two quadrants. In these two, again, if you started out here, your distance from eigenvector 1 goes to 0 faster than your distance from eigenvector 2. Your component of eigenvector 2 goes to 0 faster, so your distance from eigenvector 1 goes to 0. And similarly, if we started here, we would go this way. And actually, this is poor drawing. It's actually quite hard to draw if you have limited artistic talent. We can't quite parallel this, so it's something like this. And this describes the behavior of the system in the x1, x2 plane, whatever it is that x1 and x2 represent, and we'll worry about the physical interpretations of these systems later. But for now, we're interested in find the eigenvalues, -2 and -1, find the corresponding eigenvectors, 2, 3 for -2, 1, 1 for -1, write the solution, and then hopefully we can sketch the solution in the x1, x2 plane. You can use a slope field program to help you with those sketches, or your graphing calculator. So this is solutions of systems of two first-order linear homogeneous ordinary differential equations with constant coefficients. Come back soon for my next video. With math, there's always more.